Alright, welcome to the 2010 AP Calculus review video. So I'm going to be going over the 2010 AP Calculus exam. Let's get started. First question says, there's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates at the rate modeled by this function. It's in cubic feet per hour. T is measured in hours since midnight. And then she gets up at 6 a.m., that's pretty early, and then right away starts shoveling snow, right? And then the rate at which she removes the snow is given by this function. Obviously, it's 0 if t is between 0 and 6 because she hasn't started removing snow yet. And then this is the rate at which she removes snow after she starts. And then part A asks us, how many cubic feet of snow have accumulated on the driveway by 6 a.m.? Okay, so that means we're not going to be looking at this function, we're going to be looking at this one, right? Because this is only for the removing snow part. So we're looking at f of t, and we're looking at how many cubic feet of snow have accumulated. Well, this function tells us how much snow is accumulating at one point in time. If we want to figure out how much snow has accumulated over a period of time, we're going to be adding up all the different f of t values, and that tells us that we're going to integrate, right? So what we're going to do is we're going to integrate this function from 0 to 6, f of t dt. Alright, and then what is f of t? I'll just plug it in. It's 7t e to the cosine t dt. And if you plug this into your calculator, you're going to get 142.275. And then for units, it's cubic feet. Okay? Easy enough, right? This is a 2-point question. 1 point for the integral, 1 point for the answer. Part B. Find the rate of change of the volume of snow on the driveway at 8 a.m. Okay, so when we're talking about how much the snow is changing, we're going to look at basically the amount of snow going in, minus the amount of snow going out, right? That's going to tell us how much the total amount of snow is changing, right? Well, what's the amount of snow coming in? That's modeled by f of t. And then, what's the amount of snow going out? Well, it's modeled by g of t. Right? And if we're looking at specifically t equals 8, we're going to have f of 8 minus g of 8. What's that going to be? Well, we'll just plug in 7 times 8 times e to the cosine of 8 minus, well, if we plug in 8 into g of t, well, that's going to be 108, right? Because between 7 and 9, we're at 108. So minus 108, and that's going to give us negative 59.583 in the calculator. And then the units here, well, let's see here, it's going to be the same as the units for f of t or for g of t, and those are cubic feet per hour. So cubic feet per hour. That's the answer to part B. This was a simple 1-point question for the right answer. Okay, part C. Let h of t represent the total amount of snow in cubic feet that Janet has removed from the driveway at time t hours after midnight. Express h as a piecewise defined function with domain from 0 to 9. Okay, so basically just write a function to tell us how much snow there is. Okay? Or no, not how much snow there is. How much snow that she's removed. Okay? So, well, let's start with the easy part, right? Between t equals 0 and t equals 6, she hasn't removed any snow, right? So, we know that h of t equals 0 for t between 0 and 6. Actually, just for the sake of consistency later on, I'll just write this in reverse. So, for 0 is less than t is less than 6, no snow removed, so 0. Okay? And then, now let's look at the next section, which is from 6 to 7. Okay, what's going on from 6 to 7? Well, so originally, at time t equals 6, there's 0 feet of snow, okay? And then, the amount of snow that she removes is going to be the integral from 6 to t of g of t dt, right? Because that tells us how much snow she's removed at time t, because that's the function that this is the function that tells us how much snow she's removed at a certain time, and then we can plug in t to get the total amount of snow removed by that time. Okay? Then, since this, for between t equals 6 and 7, g of t is 125, this is equal to 125t from 6 to t, which is going to be 125 times t minus 6. Okay? So, what does this mean? From t's between 6 and 7, the amount of snow that has been removed is 125 times t minus 6. Okay, finally, we're going from 7 to 9. Right? So, this is going to tell us how much snow she's removed between t equals 7 and t equals 9, right? So, what we're going to do here is we're going to say, okay, how much snow has she removed at time t equals 7? Right, that's h of 7. We'll take this, and then we'll add the amount of snow that she's removed between time t equals 7 and some other time t. Okay? And then in this case, g of t is going to be 108, because that's what g of t is between 7 and 9. So it'll be 108 dt. Okay? This is how much snow she's removed at time t equals 7, and then this is for whatever time. So if, for example, it's t equals 8, then we'd integrate from 7 to 8. That would get us the total amount of time, total amount of snow removed from 0 to 8, right? 0 to 7, and then 7 to 8. This is going to be, well, what's h of 7? We can just plug in 7 into here, because this tells us the amount of snow at time t equals 7. If we do that, we're going to get 125 times 7 minus 1, which is 125. So it's 125 plus 108 t from 7 to t. Plug that in, we get 125 plus 108 times t minus 7. And that's how much snow, that's how much snow she removed between t equals 7 and t equals 9. So that's 125 plus 108 times t minus 7. Okay? All we got to do is put these pieces of information together in a piecewise function. So we'll say that h of t equals, it's going to be 0, right? For 0 is less than t less than equal to 6. And then for t between 6 and 7, we'll get 125 times t minus 6. That's from a little bit up here. It's from right here. And then for t between 7 and 9, it's going to be 125 plus 108 times t minus 7. That's going to be for 7 is less than t, less than equal to 9, right? And that is the piecewise function that tells us how much snow she's removed at a certain time. I keep saying snow. How much snow she's removed at a certain time t. Okay? This was a 3-point question. 1 point for each of the 3 parts of the piecewise function. 1 point for this part, 1 point for this part, 1 point for this part. Okay? Part T, how many cubic feet of snow are on the driveway at time t equals 9 a.m. Right? So for this one, it's just going to be simply thinking about how do we tell how much snow there is on the driveway. Okay? So if we look at how much snow there is, well, it's going to be how much snow was added, right? Snow added, minus how much snow is removed. That's going to tell us like the net amount of snow, if you will. Okay, so let's see, how much snow was added? Well, we know that the snow accumulates at this rate. So if we want to figure out the total amount of snow added from time t equals 0 to time t equals 9, all we got to do is integrate that function from 0 to 9. just like what we did in part A. So 7t e to the cosine t dt, right? Minus, and then, well, okay, the snow removed. How much snow did she remove? Well, that's going to be h of t from part C. That's going to be h of 9, right? I'm actually write this. It's going to be the integral from 0 to 9 of f of t dt. That's this part, minus h of 9. Right, remember, h of t tells us the total amount of snow that she's removed at a certain time t. Okay? And well, what's h of 9? If we go back to our answer that we got in part C, and we remember that from t equals 7 to t equals 9, h of t is equal to 125 plus 108 times t minus 7, 4, 7. Okay? If we plug in 9 into here, we'll get 125 plus 108 times 9 minus 7, which is 2. And then if we take this, plug it up here, 125 plus 108 times 2, that's our h of 9. We take this entire thing, put it in the calculator, and we get an output of 26.355, right? And they're asking for the amount of snow that's removed. Well, that's going to be measured in cubic feet. Okay? They said cubic feet of snow. Okay, so that is the conclusion to part D. This was a 3-point question. 1 point for this part, the f of t part. Another point for this part, the h of t part. And then the 3rd point for the final correct answer. That concludes the first question. Question 2. A zoo sponsored a one-day contest to name a new baby elephant. The zoo visitors put entries in a special box, very fancy, between noon and 8 p.m. The number of entries in the box t hours after noon is modeled by a differentiable function for t between 0 and 8. Values of e of t in hundreds of entries at various times t were shown in the table above. As you can see, I've had to make it a little bit smaller in order to make it fit. Hopefully that's not too much of an issue. In part A, we're to use the data in the table to approximate the rate in hundreds of entries per hour at which entries are being deposited at time t equals 6. Okay, so there's nothing here in the table or in the question that allows us to directly calculate the rate at which entries are being added at time t equals 6. So all we can do is, as they ask us to, we can approximate it, okay? So e of t tells us the number of entries that are in the box. We want to figure out the rate of change of that, so we're going to be looking at e prime of t, more specifically e prime of 6. This is going to tell us how much e of t is changing, so how much the number of entries are changing at time t equals 6, okay? How do we do this? Well, we don't know anything about what's going on at t equals 6, but we do know what's going on at t equals 5 and t equals 7, right? So if we were to find the slope of the graph between t equals 5 and t equals 7, and we can use that slope as the approximation for the point, or we can use that approximation for the point, the slope at the point t equals 6, right? So if we were to like graph it, for example, it was something like this. This is t equals 5 and this is t equals 7. We can use this slope as an approximation for the slope at that one point. Okay, so how do we do that? Well, we just find the slope between these 2 points, right? So it's going to be e of 7 minus e of 5 over 7 minus 5. It's going to be 21 minus 13 over 2, which is 8 over 2, which is 4 hundredths of entries per hour. Entries per hour, right? Awesome. That was a simple 1-point question. Part B, use a trapezoidal sum with the 4 subintervals given by the table to approximate the value of 1 over 8 times the integral from 0 to 8 of e of t dt, and explain what that means in terms of the number of entries. Okay, so we want to approximate 1 over 8 times the integral from 0 to 8 of e of t dt. Okay, we'll see how we're going to do that. So we want to do a trapezoidal sum, right? So that's going to be is, first of all, let's identify the subintervals in the table, okay? So the first one is going to go from t equals 0 to t equals 2, okay? That's subinterval 1. The second goes from 2 to 5, then from 5 to 7, and from 7 to 8. Those are the 4 subintervals that they're asking for, okay? And then second, let's actually calculate the trapezoidal sum, okay? So that's going to be the average of these two E of t values, right? So we're going to add the first two together, 0 plus 4, divide by 2 to get the average, and then multiply that by the difference in the t values. So we take that and we multiply it by 2, okay? And that's going to be the trapezoidal sum for the first part. That's for 0 to 2, okay? The second trapezoidal part, the second subinterval, goes from 2 to 5, right? So we're going to take the average of these two, so it's going to be 4 plus 13 over 2, and you'll notice I'm adding these two together. And I'm going to multiply this by the difference between these two t values, which is 3. Okay? Then for the next subinterval between 5 and 7, I'll take the average of these two, so 13 plus 21 over 2 times the difference between these two t values, which is 2. And then finally, I will try to scoot this over. There we go. I don't know what that is. Whatever. Okay, there we go. So last subinterval, it's going to be from 7 to 8. So the average of 21 and 23 times the difference between these two t values, 1, right? So this entire thing is the trapezoidal sum. If you integrate this, or not integrate this, but if you evaluate this in your calculator, you should get the answer of 10.688, okay? And this, what they're asking for, so here's like a little trick here. Whenever you see, this is a really common type of question where they'll give you 1 over something times an integral, the answer is always pretty much like, I can't think of really any exception, 99.999% of the time, the answer to this kind of question is going to be, it's the average value of the function. Okay, so here E of t is the number of entries. Well, this 1 over 8 times this integral, that's going to give us the average number of hundreds of entries in between t equals 0 and t equals 8. Okay, so whenever you see, if you see this on the AP exam, you see a fraction multiplied by an integral, and they're asking you what it means, it's like just write it's the average value of whatever this function is, and then here are the bounds between 0 and 8. So in this case, this is the average number of hundreds of entries in that box between noon, right, t equals 0, and 8 p.m., t equals 8. This was a, let's say, 3-point question, 1 point for setting up the sum correctly, 1 point for getting the right answer, and 1 point for explaining what it means. Part C, at 8 p.m., volunteers began to process the entries. They process the entries at a rate modeled by the function p, where p of t is that there, and it's in hundreds of entries per hour, and it's between 8 and 12, okay? So they start at 8, and I guess they go until 12. According to the model, how many entries had not yet been processed by midnight? Okay, so for this question, we're going to have to look at, first of all, how many entries were there at time t equals 8, right? Because they dropped, the visitors dropped entries between t equals 0 and t equals 8, and at the very end of all that, at t equals 8, how many entries were there? And, well, that's simply going to be t of 8, right? Because E of t tells us how many entries are in the box. Well, let's see here, at t equals 8, there seem to be 2,300 entries in the box, okay? So that's how much they're starting with, right? So at time t equals 8, they have 2,300 entries that they need to process, okay? So they start with 23, okay? And then how much are they going to process, right? Well, let's see, at p of t, this p of t is telling us how much entries they're processing at a certain time t, but if we want to, well, it's telling us the rate at which they're processing at a certain time t. If we want to figure out how many entries they're processing over a period of time, we're going to have to integrate this, okay? So we're going to have to integrate p of t from 0, or not, sorry, not from 0, from 8 to 12, because those are the times at which they're processing entries, right? So we're starting with 23, this is how much we have, and then they're removing the entries by processing them at this rate. So we'll have 23 minus the integral from 8 to 12. Now I'll just write out the p of t function, t cubed, 30t squared, 298t, 976 dt, and if you take this entire thing evaluated in your calculator, you should get 7. Okay, so what this means is there are 700 entries that still need processing. Okay, that's what they asked for, right? They said how many entries not yet been processed. Well, 700 entries have not yet been processed. Okay, this was a, let's see here, so a 2-point question, 1 point for setting up the integral and 1 point for the right answer. According to the model from part C, what time will the entries being processed most quickly? Okay, so what we want to do here is we want to take p of t, which is telling us how quickly they're processing the entries, and find the maximum, right? So remember, whenever you're trying to maximize a function, you want to start by taking its derivative and setting it equal to 0. So what is p prime of t? Well, that's going to be 3t squared minus 60t plus 298, okay? And then on a new line, we'll set this equal to 0. All right. Now, if the fastest way I would do this is just graphing it on a calculator, and then finding the intercepts. Whatever way you choose, you should get 2 different t values. T equals 9.184 approximately, and t equals 10.816 approximately. Okay, now, to find this absolute maximum, we're going to set up a table. Okay? On one hand, we're going to have t. On the other hand, we're going to have p of t. It's telling us the number of entries, right? So, in our table, we're going to have the endpoints, which are 8 and 12, and then these values, 9.184 and 10.816. And then for each of these, we're going to find the corresponding p of t value, okay? At t equals 8, it's going to be 0. T equals 12, it's going to be 8. Here, it's going to be 5.089. This just comes from plugging the numbers into the calculator, right? And then 2.911. And then, as you can see here, the highest number out of this bunch is at t equals 12, right? It's 8. So what this means is that the entries were being processed fastest at t equals 12, because p of t is the rate at which they're processing the entries, and it seems like that's highest at t equals 12. So the entries are being processed fastest at t equals 12, and this kind of chart here is your justification. So this was a 3-point question. 1 point for setting it equal to 0, 1 point for identifying the candidate points in your chart, and 1 point for the correct answer. That concludes question number 2. Question 3. There are 700 people in line for a popular amusement park ride when the ride begins operation in the morning. Once it begins, the ride accepts passengers until the park closes 8 hours later. While there's line, they move on to the ride at 800 people per hour, and then the graph shows the rate at which people arrive at the ride throughout the day. T is measured in hours since the ride begins operation. Cool. Part A asks, how many people arrive at the ride between t equals 0 and t equals 3? Show the computation that lead to your answer. Okay, so they're talking about people arriving at the ride. So that's going to correspond to R of t, which tells us the rate at which people arrive at the ride, right? So that's telling us the rate at which people are arriving at a particular time t. If we want to know how many people are arriving throughout t equals 0 to t equals 3, throughout a variety of t values, we're going to have to integrate R of t, and we're going to go from 0 to 3, right? Because they want to know how many people arrive at the ride from 0 to 3. And we don't have an actual function to integrate, but we do have a graph that we can find the area under. Because remember, an integral is nothing but an area under a curve. So we have t equals 0, t equals 3, and we have this kind of region that we need to find the area under. Right? Okay, so the way I do this is I'm just going to look at the squares. Each square is 1 by 200, so each square is 200, right? And I'm literally just going to count the number of squares and multiply by 200. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I'll just mark those off. 14 squares. And then we have these two triangular regions. If you just kind of take this one and put it over here, you'd get kind of like a square. Right? If you just take this piece and kind of combine it, move it over there, you get a square. And that's going to be another 1, 2 boxes. So in total, we have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16 boxes. So the computation would be 16 boxes, and each box represents 200 people, right? So that's going to be 3,200 people. Now, if you didn't catch that shortcut, right, where you can just move this triangle over, the other way to do it would be to, well, you can still, for the first part, you can still say, okay, 1, 2, 3, 4, 5, 6, 7, and 9. Oops, that's not how it works. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. So it would be 14 times 200 plus this triangle. Well, it's going to be 1/2 times the base, which is 1, times the height, which is 400, right? Plus 1/2 times the base, which is 2, times the height, which is 200, right? And if you evaluate this, this will also get you 3,200 people. Okay. Now, this was a 2-point question, 1 point for showing the integral and 1 point for the final answer. Is the number of people waiting to get online at the ride increasing and decreasing between t equals 2 and t equals 3? Justify your answer. Okay, so this is actually a pretty tricky question. Not because the math is hard. It's not really hard at all. There's really no math here. But the hard part is actually figuring out, there's actually a little tiny phrase in the question that's crucial to answering this question, okay? If you didn't see that little phrase, you'd be stumped. And the key phrase is that people move on to the ride at 800 people per hour, okay? So, how is that important? Why is that important? Well, let's see here. So if we're looking at between 2 and 3, right, that's 2 and 3, that's this part of the graph, okay? We know that people are getting onto the ride at 800 people per hour. So this is the rate at which people are getting out of the line, right? They're leaving the line and going onto the ride. And then this is the number of people who are coming into the line, who are entering the line, right? And you'll notice here that between t equals 2 and t equals 3, the number of people who are entering the line is always greater than or equal to 800, right? So if we're not including t equals 2 and t equals 3, looking at all the t values between them, then we can say that the number of people entering the line, given by r of t, is always greater than 800. What does that mean? Well, it means that the number of people coming into the line is more than the number of people who are leaving the line. Okay, so if we were to write that out, we see something like between t equals 2 and t equals 3, r of t is greater than 800, so the number of people waiting in line is increasing. But that makes sense, right? The number of people who are coming into the line is more than the number of people who are going out of the line, so the number of people waiting in line is increasing, right? It's like if you have more water coming into the faucet than you have more water leaving the faucet, the sink is going to fill up. Okay, so this was part B. This was simply 1 point for the correct answer. Okay, part C asks, at what time t is the line for the ride the longest? How many people are in line at that time? Justify your answers. Okay, so we know that from t equals 0 to t equals 3, so this part, okay, we know that t r of t is greater than 800, right? So from 0 to 3, the number of people who are coming into the line is more than the number of people who are leaving the line, like we said in part B, so the line is increasing. Okay. On the other hand, if we're looking at the rest of the line from t equals 3 to t equals 8, right? So from 3 to 8, the number of people who are getting onto the ride is more than the number of people who are coming into the line. So the line is decreasing. Going back to the sink analogy, there's more water leaving the sink than there is coming into the sink. So the sink is gonna empty, decreasing. Okay? So what does this mean? Well, if we were to kind of graph the number of people, or no, not the number, the size of, I guess, the number of people, and then time, well, we know that the size of the line increases and then decreases. So it's clear that the maximum number of people, so the biggest line is at the point where it switches. And it's clear that that's at time t equals 3. Okay? So line t equals 3 goes from increasing to decreasing. So that's when the number of people in the line is the largest. So what time t is the line for the ride the longest? That's at t equals 3. And now all we got to do is figure out how many people are in line at that time. Okay? And to do that, let's think about how do we know how many people are in line. Okay? That's gonna involve 3 different factors. Okay? So we're gonna have the initial number of people, okay? And then we're gonna add the number of people who enter. Now you can probably guess what the final thing is. We're gonna subtract the people who leave. You have some people enter, people leave, and if we add the number of people who enter, subtract the number of people who leave, this will get us the amount of people in the line at a certain time. Okay, and well, what's the initial number of people? There are 700 people when the line begins operation, when the ride begins operation. So the initial number of people is going to be 700. Okay, and then next, what are the people who enter? Well, if we go back to part A, how many people arrive at the ride between t equals 0 and t equals 3? We said the answer to that was 3,200, right? So the people who enter is going to be 3,200. And then what is the number of people who leave? Well, let's think about that. There are 800 people who are leaving the line per hour, okay? And so if we're going for 3 hours, the number of people who are going to leave are 800 per hour times 3 hours. That's that, okay? So 700 plus 3,200 minus 800 times 3. If you write that in your calculator, you get 1,500 people in line at time t equals 3. Okay, this was the answer to part C. This was a 3-point question. 1 point for the correct answer, t equals 3. 1 point for the correct number of people in line, 1,500. 1 point for some kind of a justification like we did here with the increasing and the decreasing thing. Part D. Write, but do not solve, an equation involving an integral expression of r, whose solution gives the earliest time t at which there is no longer a line for the ride. Okay, so what we're going to do is we're going to make up this function, right? I think this is the way that came to my mind when I looked at the problem. If it works a different way for you, sure, whatever works. So I'm going to make up this function called L of t, and this function is going to tell me how many people are in the line at a certain time, right? And we're going to draw heavily from what we said in part C, where it's the initial plus the people who enter minus the people who leave. Okay, but this time we're going to generalize it for any time t. Okay, well, initially we know it's going to be 700. That's constant, right? Doesn't matter what t is. The number of people who enter, well, how did we get that? Remember last time we integrated r of t from 0 to 3, but if we want anytime t, we're going to have to integrate it from 0 to t in general. Okay, and it's going to be r of t dt. Some people like to switch the variable here instead of using t, because they don't want this t to get confused with that t, but I don't really care. And then the number of people who leave, well, remember it's 800 people per hour, so if you want to look at it at any time t, it's going to be 800 people per hour times whatever number of hours. Okay, so this tells us how many people are going to be in line at a certain time. And we want to figure out when is the number of people in line 0. So what do you think we're going to do with this? Yeah, exactly. We're going to set it equal to 0, right? So 700 plus the integral from 0 to t of r of t minus 800t equals to 0, right? And that's actually it. This is an integral expression, right? It's an expression with an integral in it. It's an equation, and we can solve this to get the value of t where there's no longer a line for the ride. Okay? That's part D. This was a 3-point question. 1 point for the 800t part, 1 point for the integral part, 1 point for putting it all together in this final answer. That concludes question number 3. Question 4. Let R be the region in the first quadrant bounded by the graphs of y equals 2 square root of x, horizontal line y equals 6, and the y-axis is shown in the figure above. So let's label those real quick. Here's the horizontal line y equals 6. And then this must be y equals 2 square root of x. Okay? And then in part A, we're asked to find the area of R. Okay, so the key thing here to finding the area of R is this kind of distance here between the top and the bottom parts of R. Okay? So the way we figure this out is we figure out the distance from the x-axis to the top part of R, and then we figure out the distance from the x-axis to the bottom part of R, and then notice that the difference between these two gives us this white line, and that's what we want. Okay, so I'll say this white line is equal to this big green minus a little green. Alright, so this big one is going to be always equal to 6, or no matter where you are. So the top is going to equal 6. But for the bottom, it's going to depend based on where you're kind of moving around, right? And what it is, it's going to be equal to this y value, right? So it's going to be equal to whatever height you're at. That's going to be the length of that line. So it's equal to 2 square root of x, right? So therefore, this distance, this white line, is the difference between 6 and this y value. It's what's kind of left over of that 6 once you subtract the y value. Okay, so we can say that the distance that we want, I'll call it r, is going to be 6 minus 2 square root of x. Now all we got to do is integrate this from 0 to whatever this ending x value is, and then in this case it's 9. So we're going to integrate from 0 to 9, including just taking this white line, and we're adding it up over and over and over and over again, all across from 0 to 9. So we're integrating this from 0 to 9, and since this is the calculators, I'm going to have to do this by hand, right? And that's the worst thing ever. We'll do an integral by hand. Okay, so we'll integrate this. Integral of 6 is 6x, and then for this guy, this is, I can rewrite this as x, let's see, I can rewrite this as x to the 1/2, right, because that's what a square root is. So I need to add 1, I'll get 3 halves, and I'll multiply by the reciprocal, so it'll be minus 2x to the 3 halves times 2/3, which is 6x, minus 4/3 x to the 3 halves. Okay? So now all we've got to do is take this guy and evaluate it from 0 to 9, which are our bounds, right? Mark that here too, 0 to 9. Okay? So what's going to be? It's going to be 6 times 9 minus 4/3 times 9 to the 3 halves. And then notice whenever we plug in 0, we're going to make this 0 and this 0. So if we plug in 0, everything's just going to be 0. so I'm not even going to bother. So all we have left of that integral is this, and this is our final answer actually. This gives us that area that we want. Okay, this is a 3-point question. 1 point for the correct. 1 point for the correct integrand. 1 point for correctly taking the antiderivative, and 1 point for the correct final answer. Part B. Write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 7. Now, this is not y equals 6, it's y equals 7. Okay? So, let me draw y equals 7. Let's say it's like here-ish. That is y equals 7. Okay? So, since we're going to be rotating around that line, we need to draw two different things. We need to draw the distance from this line to the first part of r, and the distance from the line to the second part of r. Okay? I'll call this first thing little r. You can see that there's a lowercase r. I'll call this uppercase r, big R. Okay? Little case r, well, that's going to be equal to, this is 6, this is 7, the difference is 1. Right? Easy enough. And then big R, what's that equal to? Well, similar to the logic that we went through in part 1, or part A, this entire distance here is 7, right? This part from the x-axis to the bottom, this is 2 square root of x, right? So the leftover distance is going to be 7 minus 2 square root of x. It's this whole distance minus this white distance. Okay? So we have these two. Now all we got to do is plug this into our formula, which is pi integral from a to b of big R squared minus little r squared dx. And what is little r, big R, and a and b? Well, we know little r and big R. A and b are going to be the x points of the beginning and end. So just plugging in everything, we'll get pi integral 0, 9, and then big R squared, so it's 7 minus 2x squared minus 1 squared. And they don't want us to actually evaluate this, just write the expression, that's all. So we can call that enough. Okay, this was a 2-point question, 1 point for the integrand, and 1 point for the limits and the pi on the end. Part C, final part. Region R is the base of a solid. For each y, the cross-section of the solid perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base. Write but don't evaluate an expression that gives the volume of that solid. Okay, so volumes of cross-sections, right? So if we want to find the area of this cross-section, we need to think about, okay, so what is the area of each individual cross-section? Well, it's going to be a rectangle, right? So the area of a rectangle is base times height, right? From like elementary school, okay? And now we're to think about, okay, what is the base, what is the height? Well, let's see here. We're taking cross-sections perpendicular to the y-axis, right? So cross-sections are going to go like this, right? It's going to go whatever, how much far out it goes. And you can see that really how much it goes out, that's just the x-coordinate. So this goes out to this much, this x value goes out to this x value. So however far it goes out, that's just the x value, okay? So all we need to know is we need to know the x value. But the problem is this is giving us the y value. So we need to take y equals 2 square root of x and solve this in terms of x. So we'll divide by 2, we'll get y over 2 equals square root of x, and we'll square it to get x equals y squared over 4. Okay, so that gives us this distance, that gives us the base of our rectangle. So I will fill this in with y squared over 4, and then what's our height? Well, we know the height is 3 times the length of the base, so it's going to give us 3y squared over 4. Okay, so we multiply these together, we get 3y to the 4th over 16, right? That's going to give us the area of an individual rectangle, right? So for example, like this rectangle, and then this rectangle, and this rectangle. It's going off the screen, but so you can see each rectangle. And then we need to add up all of the rectangles, right? So what we're going to do is we're going to integrate these rectangles. So we're going to integrate 3y to the 4th over 16. Note it's a dy. And then now for the bounds, we're starting at y equals 0, but notice we're only going until y equals 6, right? Since we're in terms of y, we're not going from 0 to 9, we're going from 0 to 6. So we'll take this and integrate it from 0 to 6, okay? And this is the expression, let's try that better. This is the expression that the College Board seeks. They just want the integral expression. We don't need to actually evaluate it, okay? So this was, again, a 2-point question. 1 point for finding the area of each individual rectangle, this 3 over 16y to the 4th part, and then 1 point for putting it in an integral with the correct bounds and stuff. Okay, that concludes question number 4. Alright, question number 5. The function g is defined and differentiable on the closed interval -7, 5, and satisfies g of 0 equals 5. The graph of y equals g prime of x consists of a semicircle and 3 line segments, as shown in the figure above. Notice that this is not the graph of g of x, it's the graph of g prime of x, okay? So part A asks us to find g of 3 and g of -2. So we can't just look at the graph and go to 3 and then go to -2, because this is not the graph of g. Again, this is the graph of g prime. So how do we find g of 3 and g of -2? That's going to rely on the fact that if you integrate from a and b, g prime of x dx, that's going to equal g of b minus g of a, right? The fundamental theorem of calculus. Okay, so we'll take this idea and figure out how to apply it to this problem. If you didn't get it, try pause and try to figure out how we can use this principle to figure out g of 3 and g of -2. Okay, so if you are not sure, or if you are sure, either way, let's do this. So what we're going to do is we know that g of 0 equals 5, and we want g of 3. So 0 and 3 are going to be the bounds of that integral, 0 and 3. G prime of x dx. We evaluate this, we'll get g of 3 minus g of 0. And what's nice is that we know g of 0 is equal to 5. So when we solve for g of 3, which is going to be g of 0 plus this whole integral business, we can replace this g of 0 with 5, and all we have to do is figure out what this integral is. And well, we have the graph of g prime, and the integral is just the area under the graph. So all they're really asking here, when they're asking for the integral from 0 to 3, is the area under this graph from 0 to 3. So 0 to 3, I'll shade that area in. That's this, plus this little semicircle, or not semicircle, triangle. Okay, so it's these two little sections. So we know this, and we know this, so that allows us to figure out g of 3, okay? So what is it? Okay, well, g of 0 is 5, right? And we're adding this. So what is it? So this first quarter circle, it's going to be 1/4 of the area of the whole circle. So it's going to be 1/4 times pi r squared. R in this case is 2, right? Because we're going from 0 to 2. So 2 squared. That's this part. And then we also need this triangle. It's going to be 1/2 base height. The base is 1, the height is 3. So it's going to be 1/2 times 1 times 3. So these go together, and these go together. Either way, our final answer is this. Okay? So that is the correct answer. It is worth 2 points. 1 point for the, oh wait, you know what, I'll just say it at the end. I'll say it at the end. G of -2 is literally the same thing, except instead of 3 we do -2. So instead of the bounds being 0 and 3, the bounds are going to be -2 and 0. G prime of x dx. Integrate that, we get g of 0 minus g of -2. Solve this for g of -2, we get it's equal to g of 0 minus the integral from -2 to 0 of g prime of x dx. Okay, we know g of 0 is 5. And to figure out this integral, we should go up to the top. And the area from negative 2 to 0, let me erase this. Area from negative 2 to 0 is this part, this semicircle. And we already know that the area of that semicircle is 1/4 pi 2 squared. Right, that's from up there. So that is g of negative 2. And now I'll tell you the points. This is a 3-point question in total. We got 1 point for using the fact that g of 0 equals 5, 1 point for finding the value of g of 3, and another point for finding the value of g of negative 2. Part B. Find the x-coordinate of each point of inflection on the graph of y equals g of x on the interval from negative 7 to 5. Explain your reasoning. Okay, so let's see what we know. We know that we're looking for inflection points on the graph of g of x, right? So inflection points on g. Okay, well, we don't really know anything about g. So let's think about it. What does it mean when there's an inflection point? What does that mean, right? Well, when I think of inflection point, I think of the second derivative switching signs, right? So I think about g double prime changes sign. Okay, well, that doesn't really help me either, because I don't have any information about g prime double prime. What I do have information about is g prime. So if g double prime changes sign, what does it tell me about g prime? Well, if g double prime switches sign, that must mean that g prime switches direction. You could also go directly from the fact that if there's an inflection point on g, then g prime switches direction, but my mind goes through this thought process. Okay, so either way, you come to the conclusion that you need to figure out where g prime switches direction, because that'll tell you where there's an inflection point on g. So we're just going to look at this graph, because we have the graph of g prime, and we're just going to look at, okay, where does it switch direction? So it's going up, 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 up. Oh wait, look at that. It switched and it's going down. So it switched from up to down. So we'll mark that point, x equals 0. It's going down, 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 down. Oh look, it switched. It's going up now. Where's that? X equals 2. This is fun. I could do this all day, guys. I'm going up, 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 up. Oh no, it switched again. X equals 3. And down, 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 forever and ever, all alone. So from negative 7 to 5, we've come up with 3 different points where the direction switches. Okay, so these are the 3 points of inflection on the graph of g of x. And for an explanation, I'd say, okay, so at x equals 0 and x equals 3, we have we have g prime switching sign from increasing to decreasing. And at x equals 2, we have g prime switching from decreasing to increasing. And by those reasons, we can conclude that these are our 3 inflection points. Okay, so what I just said, you would write that down on the actual test. I'm not going to, though. So this was a 2-point question. 1 point for identifying the correct points, inflection points, and 1 point for the correct answer. The function h is defined by h of x equals g of x minus 1/2 x squared. Find the x-coordinate of each critical point of x, where negative 7 less than x less than 5, whatever, and classify as the location of a minimum, maximum, or neither. Explain your reasoning. Okay, cool. Now this question is actually quite challenging in my opinion. It's a bit out there. You've probably never seen something like it before, but either way, we'll tackle it. I'm saying either way a lot this video, aren't I? Either way, let's move on. So we want to find the critical point of h, and whenever you see the word critical point, you want to take that derivative and set it equal to 0. So our first step is going to be finding h prime of x. Okay, so h prime of x here is going to be equal to g prime of x minus, so taking the derivative of this, bring the 2 down, you should get minus x. And to set this equal to 0, on a new line, we'll say g prime of x minus x equals 0. Can you hear the cars in the background? I don't know. Anyway, so we do this and we get g prime of x equals x. Okay, cool. We got that. Now, classify each critical point as the location of a relative minimum, relative maximum, or neither. Well, we have this, but how do we find the critical points from here to classify them, right? And so this is really just a game of logic and looking at the graph and determining where there could be a point where g prime of x equals x. Okay, now, my eye sees this point right here, 3, 3. That's the point where g prime of x equals x, right? But we have to figure out where are the other points, okay? And we're going to use a bit of logic here, okay? So in this line segment from -7 to -2, it's impossible for g prime of x to equal x because x goes from -2 to -7, but y goes from 0 to -1. So there's no like overlap there. So it's not really possible for g prime of x to equal x in this line segment. And then in this half of the semicircle, g prime of x is positive, but x is negative. So in this half of the semicircle, it's not going to be possible for g prime of x to equal x. In this other half of the semicircle, however, we see x goes from 0 to 2, and y goes from 2 to 0, so there is going to be some point on this circle where x is equal to g prime of x. So there's going to be one point here, like somewhere, I don't know where. And then from here, x goes from 2 to 3, y goes from 0 to 3, those both end up connecting at 3, 3, okay? And then from here on out, x is greater than 3, but y is less than 3, so again, there's going to be no point where g prime of x equals x. Okay, so we've concluded by looking at this graph that there are 2 points. One is 3, 3, and the other is somewhere on this half of the semicircle, okay? And to figure out where on that half of the semicircle it is, we have to write the equation of the semicircle. So the equation of a circle is x squared plus y squared equals r squared. And in this case, it's going to be x squared plus y squared equals 4, because the radius is 2. Okay, solving this for y gets us 4, so it's a y squared equals 4 minus x squared, and y equals square root of 4 minus x squared. And looking at these, the positive half of the semicircle, so that's why it's a positive square root of 4 minus x squared. Okay, and if we want this to equal x, all we have to do is we'll say x equals square root of 4 minus x squared. Okay, this is kind of like the g prime of x, and so we're saying g prime of x equals x. Now we have to solve this for x. We'll square both sides. We'll get x squared equals 4 minus x squared. Add x squared to both sides. 2x squared equals 4. Divide by 2. X squared equals 2. And take the square root. X is equal to technically plus or minus square root of 2. But remember, we're only focused on this positive part. So we get x is equal to plus square root of 2. And that is the other point, other than 3, 3. X equals square root of 2 is the other place where g prime of x can equal x. So we found our 2 points. We found x equals, let's do it in white. Okay, x equals square root of 2, and x equals 3. These are the 2 points. And now we need to figure out, is it a relative minimum, relative maximum, or neither? Okay, so the way I'm going to do this is via a number line. Okay, so I'm going to take square root of 2 and 3, and this is for h prime of x, right? That's the equation of h prime of x. And I'm going to plug in different numbers between, one that's less than square root of 2, one that's in between square root of 2 and 3, one that's greater. I'm going to plug it into h prime of x, and I'm going to check the sign. That'll tell me whether what the sign is of h prime of x at that particular point. Okay, so if I plug in a number less than square root of 2, like for example 0, I'll get a positive answer. If I plug in a number in between, I'll get a negative answer. And if I plug in a number greater, I'll also get a negative answer. So what does this tell me? At square root of 2, h prime of x switches from positive to negative. So h has a relative maximum at square root of 2, because h prime switches from positive to negative at square root of 2. But at x equals 3, h prime doesn't switch sign at all, it just stays negative. So there actually is neither a maximum nor a minimum at x equals 3 because h prime didn't switch sign at x equals 3. Okay, that concludes part C. This was a 4-point question. 1 point for successfully taking h prime of x, 1 point for successfully finding the two candidate points x equals square root 2, x equals 3, 1 point for correctly stating that this relative max is square root of 2 and giving the reason, and 1 point for stating that it's neither max nor min at x equals 3, again giving a good reason. Okay, that's number 5 out of the way. Done. Alright, final question. Solutions to the differential equation dy dx equals xy cubed also satisfy blah. Let y equal f of x be a particular solution to the differential equation with f of 1 equals 2. Part A, write an equation for the line tangent to the graph of y equals f of x at x equals 1. Now, you probably have never seen a question like that before, where they're asking you to write a tangent line with all this stuff here. Maybe you have, but maybe you haven't. Either way, don't get confused by the complicated dy dx's everywhere. Just kind of take a second to focus and think about what you need to solve the problem. Okay, so to find the equation for a tangent line, you need two things. You need a point and a slope. Okay, so what's the point? Well, it's going to be, since we're at x equals 1, the point is going to be 1 comma f of 1. And the slope is going to be the slope at that point, which is f prime of 1. Okay, well, we know that f of 1 equals 2, so the point is 1 comma 2. Not that bad. And then for f prime of 1, well, let's see here. We know that dy dx equals xy cubed. That's the slope at a point, right? dy dx, f prime of x, same thing. And we know that x equals 1, y equals 2, right, from a point. So we just plug x equals 1, y equals 2 into dy dx, and we get that the slope is equal to 1 times 2 cubed, which is 8. Okay, so we have the point, we have the slope. We need to put these together, so we get y minus y1, which is 2, equals m, which is 8, times x minus x1, which is 1. And there we go. That's it. This was a 2-point question. 1 point for correctly figuring out the value of f prime of 1, and 1 point for putting the whole thing together in the point-slope form equation. No, we'll just keep going. Part B, use the tangent line equation from part A to approximate f of 1.1, and given that f of x is greater than 0 for x between 1 and 1.1, is the approximation for f of 1.1 greater or less than f of 1.1? Explain reasoning. Okay, so we'll start with the first part of the question. Use the tangent line equation from part A to approximate f of 1.1. That's just going to be as easy as taking 1.1 and plugging it into x. So y equals 2 plus 8 times 1.1 minus 1, which is 2 plus 8 times 0.1, which is 2 plus 0.8, which is 2.8. That is not an 8. 2.8. There we go. So f of 1.1 is approximately 2.8. Boom. Okay, now the second harder part. Given that f of x is greater than 0, is the approximation greater than or less than? Explain your reasoning. Okay, so the key thing you need to remember is that whenever they ask you for these kind of is the approximation greater than or less than kind of questions, the first thing that you'd always think of is concavity. Okay, so I need to think, oh, is this function f of x concave up or concave down? And whenever you look at concavity, you need to look at the second derivative. Okay, so let's draw our attention over here to dy dx. So we need to think, okay, so if my derivative is positive, second derivative is positive, my graph is concave up. If it's negative, it's concave down, right? Why am I looking at the second derivative again? Well, it's because we need to look at concavity to determine whether the approximation is greater than or less than, and when I think of concavity, I think of second derivative. Okay, so looking at here, we know that x is always positive, and f of x is always positive for x between 1 and 1.1. Okay, so since x and y are both positive, the second derivative is going to be a positive times a positive, so the second derivative is also going to be positive, right? So we know that d squared y dx squared, second derivative, is positive, So let's say so call it f(x). So f of x is concave up. Okay, so now that we know that, we can figure out what's going on with the approximation. Okay, so if I were to draw a concave up graph, and then I say, okay, so let's say x equals 1 is right here, all right? So if I were to draw a tangent line at x equals 1, notice the tangent line always is going to lie below the graph, right? No matter where I chose 1 to be, the tangent line is always going to lie below the graph. So what does this tell me? The tangent line is going to be below the actual value. So our approximation, this guy, which used this tangent line, is going to be less than the actual value of f of 1.1. So our final answer would be something along the lines of, okay, the approximation is less than 1.1 because the second derivative is greater than 0 for 1 is less than x is less than 1.1, so the tangent line is going to be below that curve. Okay, this was a 2-point question, 1 point for the correct value of f of 1.1, and 1 point for stating that the approximation is less than 1.1 with a proper explanation. Part C, find the particular solution of y equals f of x with initial condition f of 1 equals 2. I love these questions because they are just so much easy points, right? If you've seen any of the other videos, you know I love these questions. They just throw points at you like no one's business. So we have this kind of thing. We want to solve this differential equation, right? So the differential equation in this situation is dy dx equals xy cubed. So the first thing we're going to do is we're going to separate our variables. Bring the x's to one side and the y's to one side. So if I do that, I'll bring the y's to the left, and I'll get 1 over y cubed dy equals x dx. Okay? So now that I've separated the variables, my next step is going to be to integrate. Okay? This is like a memorized procedure. Separate the variables, integrate, so on, so on. So next step is integrate. The integral of x is x squared over 2, and the integral for 1 over y cubed, well, this is going to be the same thing as, let me erase this and write it as y to the negative 3, right? Because 1 over y cubed is the same as y to the negative 3. When you bring the y cubed to the top, you switch the sign of the exponent. So it became y to the negative 3. So now when we integrate this, we add 1 and we divide by that new number. We add 1 to this, it'll get negative 2, and divide by negative 2. That'll get us y to the negative 2 over negative 2 equals this plus c. Okay? Remember, for these differential equations, you only put the plus c once. Okay? Now we'll just rewrite this to make it a little bit nicer looking. We'll get 1 over negative 2y squared equals x squared over 2 plus c. And now we have to solve this for y. Okay? What I'll do is I'll bring my y squared up, and I'll bring this entire thing down. So that'll give me 1 over negative 2 times x squared over 2 plus c equals y squared. And then I can distribute the negative 2, and I'll get 1 over negative x squared minus 2c. I'll keep it as a plus 2c. It doesn't really matter the sign here because a negative constant is just another constant. This is equal to y squared. And I'm going to do a thing. So the thing I'm holding is 2c. I can just keep it as a c because it's just another constant, right? If you multiply a constant by 2, it's still a constant. If you make a constant negative, it's still a constant. So the c is just a constant. It's not, the c and the c are different numbers, but they're still constants, and that's really what matters here. Okay, so anyways, we have this. We'll take the square root of both sides, and we'll get y equals plus or minus square root of 1 over negative x squared plus c. Okay, now how do we figure out what the value of c is? Because c is a number, right? It's some unknown, mysterious number. To do that, we're going to use our initial condition f of 1 equals 2. We'll plug in 1 for x and 2 for y, okay? So we'll plug in 1 comma 2, and we'll get 2 equals plus or minus square root of 1 over negative 1 plus c. obviously it's going to be a plus, right? Because square roots are always positive, and so if we had a negative here, that would make life a little bit weird. So we know that we're going with the plus in this situation. Okay, and then now we'll move on to solving the actual thing. We'll square both sides. We'll get 4 equals 1 over negative 1 plus c. We will bring this over to the other side. We'll get negative 4 plus 4. Actually, wait, I'll say 4 times negative 1 plus c equals 1. We'll distribute the 4. Negative 4 plus 4c equals 1. We will add 4. So 4c equals 5. And we'll divide by 4 to get c equals 5 over 4. Awesome. So now this guy gets plugged back into our y. So we'll get y equals, remember now we decided it was plus, right? So I'm just going to kind of omit that. It's 1 over negative x squared plus 5 over 4. And hey, that's our answer. Okay, I do want to also mention that this is not always true for all x. This is only true for the x values where this is positive, right? So if this was negative, we'd have a negative under the square root. So it's only true for the values where negative x squared plus 5 over 4 is greater than 0. And if we solve that, we'll get x squared is greater than, or no, it's less than 5 over 4. 5 over 4. So that would mean that negative square root of 5 over 2 is less than x. It's less than positive 5 over square root 2. So you can kind of take this guy and like add that as an addendum to your answer, but I don't think it's required. Okay, so that was the end of that. This was a whopping, let's see, 1, 2, 3, 4, 5-point question. Yeah, I should double check that. Yeah, 5-point question. So 1 point for separating the variables, 1 point for doing the integration, 1 point for including the plus c, 1 point for including the initial condition, 1 point for getting the final answer. Okay, so like I said, a boatload of points. Really awesome way to end off your AP Calculus exam, and a great way to end off this video. I hope you found this helpful, and yeah, I'll see you next time. Goodbye for now.